Hanson about DefT, boosting scalability of deformable convolution operations on GPUs, machine learning at last. So he is a PhD candidate at Duke, ACE, and interested in ML acceleration, targeting dynamic workloads, as well as sparse dynamic proceeding. So please, floor is yours.
All right. So thank you guys for attending my talk. I'll be discussing my paper DefT, targeting deformable convolution. So I know a vast majority of you already know what the regular convolutional layer is in deep neural networks. The deformable convolution is actually a special type of convolution that is a form of dynamic structure. So it appears in dynamic neural networks. On the figure on the right side, you can see the comparison between the two. The static convolution keeps a static shape of the filter spatially, no matter where you move it or you stride it across the input. The deformable convolution, however, has the capability of reshaping its filter to better accommodate the input. So essentially the idea here is it adaptively samples the input for greater representation power, and it does so using a logical controller. And it doesn't introduce too many extra flops or extra parameters, so it's very attractive in terms of the theoretical accuracy benefit over the theoretical number of computation. On the bottom of the slide here, you can see that if you do some drop-in replacements of some convolutional layers on mask RCNN, for example, you only introduced 1% extra parameters and 1% extra flops, but you can significantly increase the accuracy by 10%. But there is a catch. The actual runtime does degrade by 12%, and I will discuss why this happens in the upcoming slide. Before talking about where the degradation is coming from, I'm going to break it down into what is the mechanism for performing this adaptive sampling on deformable convolutions. Essentially, there are three main stages. The last stage is what everyone's familiar with, the conventional convolutional, the main convolution. But there's two stages before that are introduced. The first one is a very lightweight convolutional layer that has the same number of output channels as the number of spatial positions there are in your kernel. So if you have a 3x3 kernel, there will be 9 times 2 output channels, and times 2 is for the XY coordinate offset. So this produces offsets for each of your spatial positions for each window. And then because these offsets are not integer, they're actually floating point, we need to perform some kind of processing on the input to generate a deformed feature map. This is where we introduce bilinear interpolation. And the bilinear interpolation essentially takes 4 neighboring pixels and does a weighted average of them. All right, so we'll move on to the first main part here, which is the motivation. So what the deformable convolution introduces is theoretically lightweight, but there is a significant cost to it. So I essentially did some motivational study here where we took a very square-shaped convolutional layer of 64 by 64, and we swooped different dimensions to reveal some trends. Some things stood out here. The main one is that it's not really that surprising. The main convolution forms the bulk of the total number of operations. And also bilinear interpolation, at the worst case, introduces about 10% extra flops. However, when you look at the second row in this figure, it actually shows that bilinear interpolation it might incur up to 35% extra operand transfers. And this translates to a terrible arithmetic intensity. And it is low arithmetic intensity workloads don't work well with GPUs. So no matter what kind of orientation we have here, bilinear interpolation ends up having at least 1 order of magnitude worse arithmetic intensity compared to the main convolution. All right, now I'm going to give you a general idea of how deformable convolutions are implemented in the current code bases. So if you were to take a look at the popular code bases MM detection and Detectron2, the deformable convolution operator is implemented using a combination of PyTorch and custom CUDA kernels. Now there's it's actually segregated into three main parts. The first one is the offset convolution, which is directly using PyTorch, which we'll call some kind of Cudian convolution. And then the second one is unavoidably a custom-made CUDA kernel to perform the bilinear interpolation. And the last one uses a cuBLAS kernel. Now they use cuBLAS because after we perform the bilinear interpolation, the deformed feature map needs to be held in the unrolled format because we are no longer using the same exact inputs for every window of the operation. There are some significant inefficiencies that this introduces. The first one is that there are potential for costly round trips through global memory because there's no guarantee that the warps that are assigned to different SMs will not access, or they might access different regions of the input feature map, and we don't know this ahead of time because of the runtime varying offsets. The second is that there are a lot of wasted movement of single-use tensors. One particular example is the offsets tensor, which is produced by the offset convolution and is immediately consumed by the consecutive bilinear interpolation. Before I move on to the way that we tackle these challenges, I want to outline some observations that we made that could direct us towards a good solution. So, the first one is not everything needs to change. As I mentioned earlier, these operations are initially implemented using highly optimized libraries like Hudian and Kublas. We don't want to get rid of these optimizations and the associated performance with them, so we really want to be careful with which kernels to target in our custom implementation. The thing that pops up to us is that the offset convolution and bilinear interpolation stages are the ones that have pretty bad relative arithmetic intensity compared to the main convolution. So that tells us that it's actually a great opportunity to select those two instead of trying to target all three kernels. And on the figure on the right side shows that those two kernels are actually responsible for up to 35% extra off-chip data transfers, which is very bad for performance because you're no longer able to take advantage of that really high bandwidth, low latency memory that's closer to the cores. The second observation is just because your workload is input dependent doesn't mean it's predictable. It's not predictable, right? So what we found is that by processing all the samples of the COCO data set, we found that it actually follows a plus distribution with a diversity that increases generally increases as we go into deeper layers. And we observed that this is actually likely a consequence of the data set structure that's built. And this is something that's inherent to the way that we train our models. Every single data set has an underlying pattern or behavior or distribution with it. And consequently, it will produce something similar to this for the offsets. Now, let's move on to how exactly do we optimize this workload. The novelty number one is actually very, very old way of optimizing workloads, fusion and tiling. But the novelty here is that we actually target the first two kernels rather than naively targeting all three. Because the main convolution is a very large operator, consumes most of the flops, and so we prefer to keep it on a very highly optimized Kublas implementation. And so the fusion will essentially resolve both of the inefficiencies in terms of immediately consuming the offset tensor as it's stored in local memory, and also trying to minimize the number of round-trip accesses through global memory by buffering a portion of the input feature map inside shared memory that could be accessed by both the first two operators. Tiling is what enables us to parallelize this fused kernel and also make sure that the relevant data can be kept within shared memory. So on the figure here, it shows an example of, although we do give up some of that performance that the baseline offset convolution can achieve, we do regain a lot of the performance that the bilinear interpolation is missing by fusing those two together. And that's where we see the green square and triangle. The second novelty is called tile padding. So there's actually two main reasons why we want to do this. Before I get into them, I would like to quickly define the type of offsets that you might encounter when performing this operation. The first one is in-boundary. So in-boundary is when an offset is within the tile that you have loaded in the shared memory, and so it's readily available for the cores to receive. The second one is called invalid out of boundary, and so this is essentially where the offset exceeds the tile boundaries, but it also exceeds the input boundaries. So essentially this data can be simply padded with a 0, therefore it does not incur global memory access. Third one is an out-of-boundary offset, and these are the ones that are bad for us because they are outside of what we currently stored in local memory, but they exist in the actual input, so we need to grab them from global memory. Now, since I've defined that, the two main reasons why we want to do tile padding is we want to be able to introduce enough parallelism, introduce enough blocks that can fully utilize the SMs on the GPU. And the second one is we want the tile shape to be large enough to accommodate the average diversity for the offsets inside a single tile. There are two contradictions that lead us to why we want to do this. The first one is deeper layers tend to have smaller input feature map sizes, so if you try to tile with the same shape, you'll end up with less blocks and therefore a chance of lower utilization on your GPU. Second one is deeper layers tend to have larger offsets, so these are conflicting behaviors. So in order to deal with that, we actually introduce a padding region that will allow it, that essentially is prefetching that data into shared memory so that it's available for the bilayer interpolation operation. There's a really quick optimization here that we can essentially enforce a synchronous load of the tile core, and that's the part that's not the padding, and then do an asynchronous load of tile padding. That way, we can perform the offset convolution as soon as possible. And then finally, how do we determine the actual tile shape that's optimal for our workload? There are some hard constraints and soft constraints. In terms of hard constraints, obviously the tile must be able to fit inside the shared memory. And the second one is tile core must encompass the entire filter shape. This is so that the offset convolution can perform in its completion without having to go through global memory. Some soft constraints is, as a general rule of thumb, we do want to have at least 2 tiles or blocks per SM in order to enable some parallelism there so that one block could theoretically do some memory operations while the other ones perform compute. And lastly, we want our tile padding to be approximately the same as our diversity for a given layer. We have a heuristic approach for tuning this where we essentially use these equations to have a first set tile shape, and then we prefer to increase the tile core size while decreasing tile padding size to reduce the amount of data transfers. And we do this iteratively before we violate either equations 4 through 6. And we have a lot of other optimizations that I don't have enough time to cover today, but if you're interested, you could take a look at more details in our paper. Now, putting it all together, there are essentially 6 stages to our kernel. First one is we load the data into shared memory. Then we perform local unrolling and offset convolution in a software pipeline fashion. And then we store the results into shared memory, which is immediately consumed in stage 5 by the bilayer interpolation. And we hopefully are able to reuse tile data, the inputted tile data in the shared memory. And then lastly, we ship the deformed input feature map into the final main convolution. All right, now I'll quickly go through some of the results. Part of the paper covers a sensitivity analysis to show exactly how, in what range of scenarios our approach can actually give us benefit. And the main key takeaway from here is that the offset convolution is typically 18 times slower, or takes 18 times less time than the BLI. And therefore, we're able to give up some of the runtime or increase the runtime of the offset convolution and reduce the runtime of the BLI. And actually, the baseline operation performs better with larger kernel shapes because we cannot support those other types of, like for example, FFT-based convolution tricks to make it faster. For the end-to-end training, we compared against a theoretical CNN type layer that introduces both the offset convolution and main convolution, but without the bilayer interpolation. And the key takeaway from here is if you zoom into the specific deformable convolution layers, we're able to achieve up to 31% of speed up, which is compared to the 46% ceiling, not bad. And then lastly, there's some ablation study that I don't have time to talk about today, but if you're interested, you can take a look at for more details in paper. So, all right, so thank you guys.